I really like the topic of this workshop, which is current research trends in civil engineering, which not only just is specific to a particular branch, rather it is, it sort of encompasses uh, almost everything related to civil engineering. Okay, so and I have had the privilege that Dr. Gattu sir has given me the opportunity to share my research area with all the participants. So again, I welcome all the participants as well who have joined here for this nice present for this talk. So today, as part of this lecture, we are going to look at some very interesting features related to granular media. Now, what is granular media? So, if we look around ourselves from our day-to-day life to the applications or to the engineering that we talk about, 50%, more than 50% of the overall commercial products are based on ground media, be it the grains, the pulses, or the rice, whatever we consume as our food, even the salt, whatever you see around yourself, the everyday chai that you are having, the chai patti, that is also nothing but your grounded media. Now, after water, it is found that grounded media is the most significant material in the commercial world. Now, there are some very unique aspects of grounded media. So the one and the most fundamental aspect of grounded media is that it is discrete in the grain scale level. If you take some some pulses or dal in your hand, you will find that they are discrete particles. Is it? Okay. Now, what happens if you try to pour it in some other container? It takes the shape of it. Okay. Now, from our very understanding of science, what we know that solid is something which does not change its shape, but a liquid or a fluid is a material that takes the shape of the container, right? So we know that we can see with our eyes that these particles, each and every particles, we can identify and segregate. These are solid particles, okay? But then it is at the same time taking the shape of the container. So it has a dual property that it has discrete in the grain scale level, but it works like a fluid or liquid at the continuum level when it is in the flowing condition. And also it behaves like a continuum when you are considering the global aspect, that when it is subjected to any type of load from the civil engineering aspect. For example, sand is a granular media. The aggregate that which are laid on the or the ballast which are laid on the railway tracks, or the bitumen binded aggregates which are given in the roads. See it everywhere. You see only grounded media. Yes, there are other material as well. For example, Gattu sir is from the structural background, so there you have to think about steel and all those things, which are continuum in nature. Although if you go to the grain scale level, you will find that these are actually grains, nothing but grains, which are connected through a organic or inorganic bonds. Now, today in today's lecture, we are going to look at a advanced method and a current research topic in the field of granular media, which is the rate dependency. Now, what is the rate? So, rate the rate at which a granular media is subjected to loading. Now, many such scenarios are possible where you see that granular media is subjected to high speed or low speed loading. It can be a dynamic type of loading in case of pile driving. It can be a repetitive but transient loading in case of railway track movements. If you consider the aggregates or ballast, which is a very very common case because of the this railway track degradation problem, which is very common, especially as we are going ahead with the high speed railway movement revolution in India. We have to be very very careful regarding the quality of our railway tracks. So that tracks which are laid on this aggregate or ballast, when the railway moves on it, so that's a repetitive loading. So the railway moves, and it's like you remember this influence like diagram we used to draw when we were in undergraduate. So that loading is continuously going one another, this wheel load. So that sort of somehow is related to the time, and time is related to the rate at which this load is coming. It's depending on the for how much time this load is being exerted onto that granular media. Now, an innovative method among them now how to understand what's happening at the grain scale level and how it is being manifested at the uh, you know the macroscopic level. So we start with the introduction. What are the working principle of the this innovative method? How we can model this granular media, each and every particles, and whether we are able to predict the overall global response from such microscopic responses. And now what followed by the applications in geotechnical engineering and other civil engineering areas, and finally a brief demonstration if possible, if time permits. Now, so this is like a typical problem that you can solve with the help of a DEM. So DEM stands for Discrete Element Method. So what does it signify? So as the name suggests that we are trying to model the discrete elements, okay? And then we are trying to capture then each and every particle motion and effect of a large number of smaller particles together when they come together, and then how they are behaving collectively. So a simulation is shown. So this is from a YouTube video. So where it is showing that this is from a sort of a segregator where some particles are coming and then it is getting mixed up. Okay, as you can see, so this is like a very common example from the manufacturing industry. So the manufacturing industry can be related to the mining industry, the pharmaceutical industry, where for example, you can think this off as a the tablets that we generally consume when we are not feeling well, or it can be the aggregates, for example. So the shape, the size, the type of the material that we are considering, all this affect the overall response. uh, so in short, DEM is a way of simulating discrete matter. The major objective is to model each and every particles at the grain scale level, and with the help of the interaction between those particles, whether we are able to predict the overall macroscopic response of one system. So we have to really solve one boundary value problem. It can be a one decompression, just like we do in our UG studies, one decompression, one-sided vertical direction loading. It can be triaxial loading, it can be biaxial loading, it can be directional type of loading. Anything or everything that we come across as civil engineers can be covered with DEM based on the the geometry, complexity of the geometry and the boundary values that we have to consider. So this is a numerical model capable of describing the mechanical behavior of assemblies of disks and spheres to start with. Because when it was first proposed, so that was first proposed, we will see that. So this particle scale numerical method for modeling the bulk behavior of granular materials and other geometries like the coals, ores, sand, rock, aggregates, etc. So it is able, as I was just mentioning at the beginning of this session, that through this we are able to capture the dual nature. What is that dual nature? That it is discrete level, but come at the macroscopic level. It can flow just like any other material. Now, the discretization of the space can be done in two ways. One, we can track the position and velocity of moving particles, just like we do in a Lagrangian system, as you can see here. Switch it on. Yeah. So in a Lagrangian system, we have a discontinuous classical mechanics interaction, just like Newton's second law of motion is followed, where force equal to mass into acceleration. And then resolution is at the particle scale level. So we are not going inside the particle, but we are limiting ourselves into the grain scale level. If you consider molecular dynamics, for example, which is a step below that, even below the discrete element step, where you are actually more trying to model this molecular level phenomena, and through which you are trying to see that how a particle will behave at the particle scale level. If you go to the continuum level here on the Eulerian side, which is like a Eulerian, so here we are not track in the Lagrangian system. We are trying to track the position and velocity of moving particles. Okay, here we are trying to track the velocity at fixed grid locations. So at these locations, which are generally known as what? These are nothing but the nodes in a continuum case. So what can be a continuum? For example, a finite element method. Okay, so finite element method, what we are doing, we have our domain, and we divide it into, discretize it to small elements, and where these elements connect, these are nothing but your nodes. Okay, so we are not exactly trying to figure out how one element is behaving. Yes, we are doing it, that how one particle deforms and all, but we are not sort of considering the movement or changes in each positions of this each element. Okay, these positions are kept safe. Now, how this stress and strain are correlated? Here we are doing it with the help of a constitutive equation. What a constitutive equation does, it gives, if you're considering, in case of, now I'm talking about this one, if you're considering a continuum case, so you apply a load. So you can have two scenarios, all right? You can have a load controlled case where you are applying the load without considering how much deformation your system is going to have. So that's a load controlled case or stress controlled case if you divide it with the area. You can also have a deformation control or strain control test where you say that, okay, this is our system, and this is the the system will deform until this maybe some millimeters or centimeters based on the scale of your system. So these are the two cases. So here, once you give the load, so one has to be known. So you give the load, and then with the help of the deformation and constitutive equation, you find out the deformation. Or you give the deformation or the strain at the beginning, and then you, from that constitutive equation, that is the reverse one, uh, so this is like the generally we consider, let me see if I have this. So suppose you know the stresses, so this is your sigma and this is your strain. So if this is known, and you have to find out this one, and how they are correlated, this is a stiffness matrix system. Okay, so if you are considering a Cauchy stress space, you can have technically 9 parameters starting like this. If you are considering a coordinate case where it's x, y, and z, so you can have sigma xx, and then sigma xy, sigma xz, and similarly for all of them, sigma yx, sigma yy, sigma yz, and so on, and finally sigma zz. Now based on the this conjugate principle, you can consider like sigma xy equals to sigma yx, so that can be considered. So if you do this, so this one and this one becomes equal, so you are essentially left with 6 parameters: sigma xx, sigma xy. Sorry, I'm using my mouse for writing this, so it may look little scary. So this is sigma yy and sigma yz and sigma zz. I think everything is covered. So similarly, so this is like the sigma matrix, and then you can have a D matrix. We call it, in case of linear elasticity, we call it what? We call it the linear elastic or Young's modulus if you are considering only linear elastic case, one dimensional. So and then you can have a D matrix. So if it is 6 matrix, similarly you can have a epsilon matrix as well. Okay, So it's like corresponding to this one-to-one mapping for each one of them. And then this will become this engineering strain in terms of gamma, if you consider it. So you can have a 6 by 6 stiffness matrix. Okay, sorry for that. Okay, so all those are can be calculated with the help of constitutive equation. But here in this case, we don't have to do all those things. What do you have to do? Suppose this is your case. We will see this. Suppose this is your geometry, and this is, so this thing is inside your box, for example. Okay, you simply put a load. Okay, so the load gets transferred to each particle. So what you know, we will see this in the next. So okay, let me just finish it off where I started. So and then this force get transferred to each one of them. So it has some force, it is interacting with other contacting particles. For example, these particles are not in contact, but eventually they will come closer and start interacting with each other. So this will put force on here, and this will put force to the other side, like this. So each particle will have one normal force and one shear force at each points of contact. And if you know the force, okay, and you just use this formula. Okay, so you know this one, how much you have to give. So you know the force. Okay, so you can calculate the acceleration on each particle at any given time t. So at t plus del t, suppose that's your basic discretized time scale that we are considering. So uh, you can calculate what would be the acceleration at the next time step. You integrate the acceleration, you get velocity. You integrate the velocity, you get the movement of each particle at each condition. Now, what is unique about DEM? Each particle has its own rotational, positional, radial momentum vectors that we just talked. So it can have, it can move like this. It can go rotate. It can have the radial vectors. Okay, which side it will go, and it can also have a particular momentum. So the simulation consists of primarily three parts: initialization, time stepping, and post processing. Small time steps must be used as solution is only conditionally stable. Okay, why? If you are not using very small time steps, we will see what is the problem with that. So it is ideal for modeling separate discrete particle simulation like colloid, granular mediate, granular matter, powder, bulk materials in storage, progressive fracture, and failures. Okay, so anything and everything related to the granular media, even rocks. Rocks are nothing but granular media. Apparently, it is. You can feel like this is a solid mass, but if you break them down, aggregates are byproducts of rock itself. Okay, so industrial applications can have multiple cases, multiple areas: chemical industry, pharmaceutical, ceramics, metals, etc. uh, so we are advantage is we are modeling the movement of individual particles. Micromechanical level analysis can be done. It can be coupled with FEM, CFD. Even I have to add one more. Here it is molecular dynamics. Okay, so you can add this too. Now, what are the disadvantages? Complex particle geometries and arrangements. So that's like a sort of a tough nut to crack, because if you look at here, we have considered what only circular particles, but in reality, these particles are not circular in nature, right? They can have any shape. Okay. Now, yes, we can do it with the help of some bypassing techniques. So you can actually model exact looking real like particles, and then you just keep following the same principles of DEM. Then the complicated validation process, as the name as here, you just give the values which are required, e value and everything. You can get it from where? Doing some regular exercise experiments. But here, grain scale experiments are very tough to do. You cannot have a one particle scale. Just suppose you're considering a salt particle, so you cannot load it, because you need to have a very advanced system to load such a tiny particle, right? So, and then to get the load strain curve and then try to calibrate it, it's a very tough process. Okay. And then obviously computationally expensive. Why? Because I know as the at the beginning, you consider, for example, a 1 meter by 1 meter sample. Generally, we do it in laboratory scale. If you're doing it on sand, can you imagine the number of sand particles will be there in 1 meter by 1 meter by 1 meter cubical sample? Okay, it will be in few millions. Okay, but with the existing setup that we have, or whether it's uh, how to say that wise enough to really model 1 million particles to start with, is it wise enough? Because or is there a better way to represent 1 million particles with maybe 10,000 particles? Okay, and for that we need to go for the calibration and validation process. So if you try to have a look at how DM evolved over the years. So first, this guy, his name is Kundal. I feel lucky to have met this guy in a conference. So he developed DEM to assist with modeling of rock mechanics. Okay, so he started, this DEM to understand each and every particle movement, how it was affecting the rock behavior. Started way back in 1971, almost half a century back. Then he converted this modeling scheme into a Fortran code, and that's a very famous paper from 1978, where he actually, and that the initial code name was termed as ball. Okay, so that's the first DEM code which was developed. Meanwhile, in 74 also he came up with a in between code, and then Kundal and Hart developed codes to perform 3D DM simulations, and then eventually it got evolved over the years, and then this discontinuous deformation analysis was developed by Shi in 1992, which is required. Suppose you were to model this fracture in a rock case. So for all those cases, you have to do the this fragmentation or deformation analysis. Now, as I was discussing, so we are even, essentially solving Newton's second law of motion. So Newton's second law of motion is based on the conservation of momentum, right, and the particle motion. So we have to have a force displacement law, okay, which is dependent on the stiffness and the friction. Okay, so for from force displacement law, we calculate the force boundary condition. Suppose, let me see if I have it. Okay, okay, okay. Maybe I will just explain those in later. Suppose two particles, so one particle, another particle, they are coming closer. So this is like they are coming. So this is particle M1, this is particle M2, and they are having different radiuses. Suppose this is R1 and this is R2. So they are coming closer, coming together. And then what will happen? Can anyone tell if this particle come in contact? Suppose they come in contact at a certain time period. What happens here?
So
Can anyone?
exchange of momentum exchange will happen, I think.
Yes. So
Some
momentum exchange.
contact.
Yes. So this momentum transfer, along with the momentum transfer, depending on what type of collision that we are considering. So suppose I remember in class 11th or so, we used to read something called elastic restitution, where if you put a ball into the hard surface, it keeps bouncing, and based on the damping and all, so eventually it will go like this, and then suppose it goes like this. Okay, but then here what's happening? So the next slide is based on that. So based on whether we are considering a rigid particle or a hard sphere. So what Professor Gattu was mentioning, if you consider two hard sphere or rigid sphere. So what do you mean by what we understand from a rigid particle? So there will be no deformation. So two particles will just come and collide, and then they will just return back the other side. Okay. So if they are coming with a velocity of v1 and this is coming with a velocity of v2, so now it will have a momentum transfer. So this will give its momentum to this one, and this will give its momentum to this one. So that's for hard sphere model. Okay. So does it really occur in a real case? No, because in general, in reality, these particles are not rigid. Because if they were rigid, there will be no crushing. Okay, there is no point of a particle getting broken down into pieces if those were rigid. So in reality, these particles are soft. So whenever we are considering soft particles, okay, so whenever they come in contact, so this particle, when it comes in contact, so there will be what? There will be an overlap. Okay, so one particle, so this particle will be like this, and the other particle will be like this. So some overlap will be there. Okay, and this overlap, how much they're going in. Okay, suppose this is our delta. Okay, and how much delta will go in will be decided by the stiffness of each particle contact. Okay, so in contact, if you consider, so we can consider, if you consider a spring, suppose this is your k in the normal direction, and this is your delta force, that suppose this much of uh, no overlap has happened. So what would be the force on that? Anyone?
It will be K delta,
Yes.
K delta.
Yeah.
In
So considering a linear force uh, and deformation relationship, that should be our K. Okay. But we can have a nonlinear relationship as well. Suppose this is your delta, and then so the relationship can be F equals to K to the power delta to the power 3 by 2, for example. Or you can have a stiffness also, some quotient, something. Okay. So this is like a nonlinear force displacement equation, which is known as Hertz. Sorry for that. Hertz Mendeleev uh, this contact relationship, and this is like the pure linear contact relationship. Okay, linear contact. So we know so what we know, so based on the overlap, considering this is a soft sphere model, so we can decide like on each particle. So each particle will be having, it's not a case like when we are considering a hard sphere case, we can have only one contact at a certain event of time. Okay, we cannot have multiple contacts. But in case of a soft sphere model, we can have one particle in contact with several other particles, just like what's happening in case of the real case. So suppose this is like the particle that is under consideration, and this is the from different sides it is getting forces. Okay, so these are the forces. So what we do, we just calculate the normal forces, okay, based on this K delta equation. Similarly, we can have a sliding type of relationship also. So this particle can also slide like this, right? Okay, it's like the friction. So that is controlled by the frictional quotient, which is like this mu, and also, and this is if you consider in the normal direction as kn, we can have a shear stiffness as well. Okay, which is again F equals to ks into delta, or in delta, not in like normal direction if there is some deformation in the shear direction. Okay, so that along with the friction will control how much slip will occur in that cases. So once we know the forces on each particle, okay, so we know the force, we know the mass, we can calculate the acceleration on each mass, which can be calculated integrated once over the period of time. Okay, it can be integrated twice, which gives us the, you know, the how to say that, the translation. Okay, that at each time step, next time step where this particle will be. Similarly, the same thing can be done with the help of the rotational momentum equilibrium. All right. So rotational will give us, one will give us in the XYZ direction, that is the translation. Other one will give like how much, suppose this one will, how much will travel this side and how much it will travel in the rotational side. So we can get the omega, that is the rotational velocity, and from there we can get the theta, and also we can get the, I'm not sure, I think alpha is the rotational acceleration if you consider. Okay, so these are the disadvantages of what sir said, exchange of momentum, and these are all impulsive forces for the hard sphere cases. For soft sphere, rigid particles, but with small overlap is allowed, evaluates forces accurately, simultaneous contact are possible. Okay, so this is like the same case of instant contact and no overlap in case of the hard sphere model. Okay, and here you can see some overlap happening, okay, here in this range. Okay, so here also some this post contact will do go in, they will go in the other side, but then yeah. Okay, okay, so these are, there are some input parameters that we need to define these particles. So it can be the Poisson ratio, density, shear modulus, okay, and then contact parameters between the particle, coefficient of restitution in case of hard sphere model, static friction, rolling friction, and then between particles and geometry, just like that. Suppose you are considering some boundary particles, some particles are here at the boundary, so they will be interacting with the wall as well as on the other side to the particles. So these models, we will see a real problem and what are the parameters that I took to model one my case. Okay, so that one was like for the rotational cases, I alpha. So I alpha is nothing but your d omega dt, and then it can be solved over the entire 360 degree to find out at each time step. Okay, and this is for the translation of particles. So this is for this conservation of rotational momentum, and this is for conservation of the translational momentum. Okay, and this is like the famous force mass acceleration relationship. Okay, so where these are the different forces which are possible. Okay, so Fg is the gravitational force. If you are considering gravitation, we can have gravitation on off based on the condition. Suppose you are modeling something on lunar regolith, for example, so obviously you will change this value. Okay, and then you can have this contact forces just like this, and you can have non-contact forces. What can be the non-contact forces? Can anyone give some idea? In case from the perspective of granular media, what can be a non-contact force? Contact forces you have understood, right? We have tried to see, so any force which is being exerted on one particle because of the contact is the contact force. Now what in your assumption or in your idea can be a non-contact force?
Some electrical electrical
Yes,
magnetic
yes,
and magnetic,
yes,
that's
yes. So
non-contact.
it can be this electrical charge, but suppose you are considering this uh, you know if you are considering without any electricity, other non-contact forces can be just like a drag force, for example, right? So suppose you are considering, at the beginning we mentioned that DEM can be modeled coupled with what? CFD. CFD stands for what? Computational fluid dynamics. Suppose you have a box full of particles, okay, and then what you have? You have water in between, okay. So if you have water, so that water or any other fluid will have a drag force once it is applied, uh, experiencing some amount of force. So we know that in case of geotechnical engineering, we call it pore water pressure. All right. So that pore water pressure will have a drag force. Also, if you're considering unsaturated media, for example. So in case of unsaturated media, you have the suction. okay, which gets developed over the period of time, and that also gives some sort of extra force, drag force to those particles based on the how much voids are available for the unsaturated media to increase the porota pressure. So that's how this non-contact forces can also be modeled. And then these are all exerting the force on each particle. We calculate overall forces on each particle. We calculate this, solve this equation, and then finally we get the translation as well as the velocity of each particle. Okay, and then this was the thing that I was mentioning about. You not only can have a stiffness, but also you can have a what? Can anyone tell what is this? F equals to Kn delta N,
Damping.
and then, huh? Yes, yes. So this is nothing but our damping. So damping we need because we have to, sort of consider the energy aspects of it as well. Okay, if there is some energy dissipation occurring because of frictional dissipation or other dissipations, in order to make it more and converge it fast. So as I was mentioning that eventually any particle will eventually go like this. Okay, because of damping. Okay, so that can also be added in series with the stiffness matrix, and then you can have a tangential direction, same thing. Okay, so the particle can have a normal movement like this in this direction, and also the particles can have a frictional dissipation in the tangential direction. Non-contact forces can also be the gravitational force, not the gravity, but also the, if you're considering some other extraterrestrial forces, so it can be added. So this is also a non-contact force. You can add it separately along with the other non-contact forces that we have discussed, like the drag force or what Professor Gattu mentioned about the electrical charges. Okay. So at each time step, what we are trying to solve, we are trying to solve. Also, this is nothing but your, can anyone tell from which series we get this? What is the name of
Forward
this
oil.
expression?
Taylor series.
Yes, sir. So this is nothing but our Taylor series expression. So which is xt plus del t. So any function at the next time step, how to find out, and any next uh, independent variable can be carried, found out from xt plus. So vt is nothing but your dx dt into your del t or h. You can have other higher order terms as well, but for simplicity, we are not considering those. Similarly, you can find out this. So we know this from the very first equation, right? F equals to what? M into A at any time step t. Okay. So if you know this, you use this to find out the velocity. You use this velocity here to find out the updated position. Until now, this is clear, right? In no, it should not be a problem. So and then it gets integrated, like iterated over the time period that we are considering. So xt, then t plus del t, t plus 2 del t, and so on. Okay, like this. So the particle interaction can have the contacting particles, which can have elastic contact, and then elastic contact can have a linear and nonlinear model. In nonlinear model, we discussed you can have a nonlinear spring, Hartsman lane, Hartsman plus JKR, another type of model, and a DMT model like that. You can have an inelastic contact as well, linear spring dashpot model, hysteric model, Thornton model, etc. So these are different models to say that how these two particles will interact at this position. Okay, and we can also propose our own models such that you can model it in a more realistic way. And non-contact forces also can have van der Waals forces, liquid bridge forces, electrostatic forces, what Professor Gatto mentioned about. This one I mentioned about, then van der Waals forces if you're considering really smaller particles. Okay, so contact particles, the overlap can be calculated from this. So if this is your d value, okay, this center to center distance. Okay, so the overlap can be calculated from this equation, R1 plus R2 minus D. Okay, and then you can also have our damping forces if possible, cohesive forces. So linear, this is the linear spring model, this is the non-linear spring model. Just like that, you can have different correlation between the force and the delta. In between, you can add different types of parameters to make it more realistic. This is the JKR model, where you have some negative tension side as well in the side. So I'm not going into detail of it. These are all empirical correlations. So based on the requirement of the type of the material that you are using, we can model it. And this is like the finally DMT model for modeling particle contact models. So this is the typical schematic diagram of how two particles. So you can see that you can have a in the tangential direction these two, okay, that will control how this contact will behave, and this controls the normal contact. Okay, so and also you have a frictional contact at this position which controls the frictional dissipation. Okay, and this is the typical historic model for loading and unloading type of material. Suppose you have a particle where you want to see that how this dynamic, what is the dynamic behavior for all those cases, practical cases, we use this historic model. Okay, this is like Thornton model, but that this this is like linear. Coming back was also linear. Here, the going is linear, but then unloading is more or less non-linear. Okay, so eventually the workflow works like that. We first identify the contacts. From contacts, we get the forces. Force gives us the acceleration. Acceleration gives us velocity. Velocity gives us position. Again, it is updated in the next time stage. Then identify new contacts and then again repeat the same process. Okay. So there are multiple numerical solution software for DEM. Just like there are open source versions. We can write our own codes in DEM, just like C, C++, Fortran, MATLAB, whatever it is, Python. Okay, so one of my students is currently working to develop its own Python code based on DEM. Okay, and then there are some other cases just like lights and lamps, etc. And then we have some commercial softwares also, like EDEM. Okay, similarly Abacus. Abacus is also having a small module for DM, Rocky, and obviously PFC. Okay, so these are some of the commercial and open source options, alternatives available for DEM. Now coming to the real problem that we solved as part of it. So this is a typical stress and plot for different rate effects on a particular granular and bonded and unbonded geometry. So bonded means like rock and clay, etc. So if you put like different loading rates, so this is like a system, and you are applying the load. If you apply at different loading rates, A, B, C, where you can think like uh, A is greater than B and all. So it should follow different paths. But in case of sand and aggregate, it is believed that they try to follow the same route, even if you are applying the same, same material with if you apply different loading rates. So that's true if there is no crushing. Okay, we will see how this is true. But if the moment we talk about crushing, the entire scenario changes. What happens? Suppose this is like a particle that we are considering. So this is the particle that we are considering, which is in contact with other particles, just like that. Okay. And then it is being subjected to external load. This external load gets heterogeneous distributed around the particles. Okay. Stress waves pass through the grain contacts, as we just discussed. Okay. This particle breaks into smaller fragments, just like what happened. So it has fragmented down. The newly generated particle, because of the crushing, it destabilizes the existing contact force network, what we have initially. So that newly generated particles will try to what? Try to attain a new level of equilibrium, right? And to minimize its energy. It's the principle of the nature. And it will try to reorganize at the grain scale level. During that reorganization, and to achieve a finally stable you know grain contact force distribution. This time lag between the wave propagation and the rearrangement which is happening at the grain scale level, it leads to the rate effects. So we have actually for this analysis considered only the quasi-static case. Quasi-static case means when the rate of loading is really low, where the inertia is negligible, and multiple instances are possible. I have already discussed some of them. Uh, Energy piles, soil fluid coupling in case of a dam, high-speed railway movements, fault failure, or in a slow failure, or even the retaining walls or false slip, etc. Multiple cases are possible where particle crushing and transient loading are present at the same time. So that actually motivated us to model it. So this is like a typical DEM sample. This is the boundary that we talk about, and which is populated with a lot of particles in order to ensure that our system is in the uh, there is no boundary effect. We checked one value called scale ratio, which is nothing but the minimum dimension of the specimen divided by the D50. D50 is the 50 percentile grain size distribution diameter percent. So the algorithm we have already discussed. This is the typical uh, linear spring dashboard model, the simplistic model that we considered. And these are some real parameters that we considered. So we considered like a density of particle as almost 2650 kg per meter cube. Particle radius is this much, and initial porosity of 20%. Number of particles is around 2000. Normal and shear stiffness value same. Okay, interparticle friction is 0.6. Largest grain radius is 0.003, maybe this one. Okay, and the minimum initially it's this one. Okay, and material tensile stress when it will break down is considered to be 14.5 MPa. Okay, for individual particles. In order to ensure how strain rate and crushing are strain rate are within the quasi-static limit, we checked this inertial number concept, and we found out that our system is in the quasi-static phase. And this is like the initial sample which we showed here. This is the same sample, and this is the end sample. So what we chosen, so this sample was applied here from top and bottom. Okay. So that we consider two rates. One is 0.2 per second. That's the strain rate, which is around, if I'm not wrong, it was around 0.015 meter per second. And I think 1.5 meter per second. So these are the two velocities at which these two walls were moved towards each other. Okay. And which equivalent to 0.2 per second and 20 per second based on the height of the sample. Maybe I need to check it, but it should be that one. So this is the end result for the low rate case. This is the for the high rate case. This is like a zoom version. What's happening here, for example, this is like the zoom version. You see that one particle has broken down into. So initially, everything was white, and then as these particles are breaking down into smaller fragments, I have increased the uh, you know the change the color. It has become darker. So one, this is the first generation, second generation, third generation, fourth generation, and this one is the tiny one is the fifth generation. Okay, so which is so 0 to, so even, so it starts with 0, so not like 0, so it starts with 1 to 5. Okay, but on the other hand, for high rate cases, you see only maybe 1 or 2 generations, maximum 1 generation, hardly, maybe I can see here maybe second generation. So if you see, this is like the breakage criteria that we talked about, and this is what the end product for stress strain, no, the grain size distribution. This is the initial for this one. Okay, okay, I don't have this one, but okay, initially, so this one belongs to this one, and this one is for this one, the low rate, and this is for this one. Okay, so if you see in terms of macroscopic response, we consider two cases when there is no crushing. We put up very high values for to the particles such that they will not crush. Okay, and to our astonishment, we found out that the samples where we allowed crushing, when we superimposed these two, these two graphs into one. So there are four curves. This was for without crushing. This is for without crushing high rate. They are trying to reach the same stress level at the end of the analysis, right? But here you see a huge gap when there was crushing. So the crushing was responsible for a lot of discrepancy in terms of the macroscopic response. In fact, this when we superimposed, we found out that the crushable sample was actually showing a softening type of response. That is, it was losing strength. On the other hand, the high rate sample with respect to non-crushable sample was showing a hardening type of response. That is, it was gaining strength. It was again confirmed from this void ratio versus mean stress plot, which is E-log P sort of plot, that there was a softening here and there was a dilation type of behavior on the other hand. Now, what was happening at the grain scale level? So we found out that the low rate sample, here you can see this is the same plot here. Okay, so suppose if you consider two cases, so these two cases, so this is for the high rate and this is for the low rate case. So if you see, these two are at the same stress level, which is around, if I'm not wrong, it's around 600 kPa. Okay, so interestingly, you see that these two cases, if you see the contact force distribution, this is for the low rate case and this is for the high rate case. We see that at the grain scale level, that the contact force distribution is homogeneous throughout the system. Okay, so what it was saying that, okay, more and more number of particles were able to create contacts because it was compressed slowly. The particles got enough time to create contact, and since they got enough time to create contacts, so they were actually carrying same amount of load was carried by maybe 100,000 particles here. On the other hand, you see some areas here for the high rate case where there is no contact at all, because these particles were compressed fast. Only few particles at the top and bottom were able to take up that load. So only few particles were take up the load, and then we saw some boundary breakage happening. But because of which, this more and more number of particles were taking part, and then they were crushing more as well. We saw here. So they got enough time to rearrange, and the overall stress, there was a drop in the stress, as you can see here. Here, it led to the densification, right, and the hardening, which resulted in the strength gain in case of the macroscopic response. So this motivated us to do further analysis, just like 1D compression. We also did some isotopic compression where all the walls were moved towards each other, just like this. And that is interesting study when there is no non-crushable sample. Okay, you said that at the beginning we mentioned that sand or other unbonded material in absence of crushing, they do not show any rate dependency, right? We mentioned. So here also you see that if you consider different loading rates, they are not showing any rate dependency. But on the contrary, for the crushable sample, we saw significant differences. We also modeled it using triaxial. So this is like a triaxial sample in 3D. We applied different loads with different confinements, and we eventually get our critical state line, which was also found to be affected by the applied loading rate related crushing. Based on that, finally we applied this a constitutive model, okay, which was based on the breakage mechanics principle, and then we were able to qualitatively capture the rate dependency for drained as well as for undrained responses. Okay, with this I conclude. Let me see if I can show you something.